Okay, now let's say you have a long, straight electric power line coincide with the x-axis, and it carries a uniform line charge density of about, let's say, 1 unit coulomb per meter. Okay, now we want to know what is the electric field on the y-axis using the approximations that the wire is infinitely long. Okay, so I'm going to draw it in an x-axis. So this is my x-axis. Because infinitely long, I can pick one point as my reference point for my y-axis. So that's my y-axis. And then to solve this problem, I know that this has a uniform charge on it. Let's define this charge density lambda, which you can estimate it as to be dq divided by dx. What does it mean? It means any little pieces of dx of line you pick, it has some dq charge on it. So this little tiny part of the wire, dx, has dq charge on it. Now, because of this problem is symmetrical, I can always, with respect to the center, I can pick another point on the other side of that reference point with the same amount of charge, but on the same amount of length, but exactly in the opposite to this first dq. So if dq is at x from the origin, this part is minus x from the origin. And then let's say the question asks you to find the electric field on this point, on the y-axis. Okay, how do we solve it? For any point charge, I will have an electric field like this. So it would be in this direction. So that would be dE, the vector dE to the right. The charge on the right side then will have a electric field in the opposite direction. I'm assuming that both charges are positive. Okay, so dE. Now you can go ahead and break this to the components. So first of all, let me say that I want to know how much is the electric field at this point, which is located at some distance y. This triangle is a right triangle. This is 90 degrees. If I know what is this theta, then I can also know what is this r, the distance between dq and the point of interest. So I would have r would be equal to, in this scenario, x2 plus y2 to the power of half. I can also know that the sine of theta is this x, the opposite to the angle theta, divided by r, which in this case is x2 plus y2 to the power of half. And then I will also have cosine of theta, which is adjacent to the angle theta, which is y, divided by r, the hypotenuse, which is x2 plus y2 to the power of half. Okay, so I already know these things, but I can break this vector dE based on its components. So it will have two components, one in the x-axis, one in the y-axis. So we will have dE sub x, and then we will have dE sub y, which is upward. For the dE in the left side, I can also break it into two components. So there will be dEx, but in the negative direction, and then there will be a second component, dEy, which is upward. Now, as you can see, if I go ahead and add another dq in the right side, there will be also similar dq's on the left side. So the x components always cancel the x components of the electric field. So this electric field and this electric field will always cancel out. And the only thing remains is the y component of this electric field, which adds it together. Now let's just see how much is that y component. If this angle is theta, then this angle will be also theta, and this component would be the dE cosine of theta component. So the dE sub y would be dE times cosine of theta. And that's why we needed to know what the cosine of theta is. So what I need to calculate is this quantity, okay? Knowing that dE is only related to the dQ and this R. So I can always say dE is the K, the electrostatic constant, times dQ, the charge, the source of that dE, and then R to the power of 2. And going back to here, you will know that the R is x2 plus y2 to the power of half. So I can replace it here right away. x2 plus y2 to the power of half to the power of 2, that becomes to the power of 1. And then you have dEy is dE times cosine of theta. So let's just go ahead and calculate dE sub y, then would be k dq divided by x2 plus y2 multiplied by cosine of theta, which is y divided by r. So it would be multiplied by y x2 plus y2 to the power of half. There's also this idea that dq would be related to dx through this linear density of charge, lambda. And so I can go ahead and replace dq. So k dq becomes lambda dx times y. Then I can combine these two denominators together. That becomes x2 plus y2 to the power of 3 by 2. Okay. Now, if I want to know what is the electric field in the y direction, then I need to integrate. And remember, I need to go from minus infinity to plus infinity for one of them, one of these dEs. Or if I go from 0 to infinity, then I have two components added together. So I'll go with one of them. And the x component obviously cancels out, so I don't have to worry about it. And so I'll go from minus infinity to plus infinity over this dE sub y. Now, in that case, k, lambda, and y are constant. I'll bring them out of the equations. So, and then the only thing left behind is dx in the numerator and x2 plus y2 to the power of 3 by 2 from minus infinity to plus infinity. Now, if I know what is the solution to this integration, then I can solve this one. I can solve this equation. Okay, if you go to the back of your book in the appendix, you will see that this integral is solved for you and the answer would be provided to you. Except in our equation, we have x2 plus y2, not x2 plus a2. So let me just rewrite this equation to be exactly as we have it. So we will have dx divided by x2 plus y2 to the power of 3 by 2. And this would give us plus x divided by y to the power of 2 root square x2 plus y2. So this is going to be the answer that I'm going to use in my previous equation. And so having this solution, then E sub y then would be k lambda x divided by y root square x2 plus y2 when you calculate it from minus infinity to plus infinity. Okay, now we need to calculate what happens at infinity. So when x goes to plus infinity, then one can say that x2 plus y2 is the same as x to the power of 2, because y is just a constant, but it's not infinity. And also at the same time, when it goes to minus infinity, you will still have the x2 plus y2 is equal to x2. So in both cases, I can say that the denominator simply becomes x to the power of 2. Okay, now let's just replace it. So when x goes to plus infinity, I will have k lambda x divided by y, and then root square of x2 would be absolute magnitude of x, but I am in the positive side, and so it would be the same as x. So I will replace it with x here. Minus, when x goes to minus infinity, then I will have k lambda. Now, at this point, x is a negative value, so I'm going to replace it with minus absolute value of x here to remember that when x goes to minus infinity, it's always a negative value. Absolute value of x is a positive one, divided by y, and then root square of x2 is always an absolute value, a positive number. Okay, the absolute value cancels absolute value. The x cancels x. And so we will end up with k lambda divided by y minus and another minus plus k lambda divided by y, which becomes 2k lambda divided by y. And so the electric field around an infinitely long wire would be simply 2k lambda divided by y.